kind introduction and welcome to my presentation. So the work I'm going to present today is a security extension for distributed version control systems, and this is joint work with Michael Lass from the University of Paderborn and my colleague Christoph Sorge at Saarland University. So I guess everyone here knows what version control systems are, but a bit of context might be appropriate anyway. So the goal of version control systems is to track changes to documents in a way that each version of a document can be recovered later on. And for this, all versions of documents are stored in some database, the so-called repository. Now, these systems usually allow different users to work together on some project, and for this, write accesses of different users are coordinated by those systems, and to be able to deal with lots of revisions, these systems do not store document versions in their entirety, but only actual differences between document versions. Now, the classic VCS are the concurrent version system and subversion SVN. And these have a centralized architecture, so we have some central server that stores the database, the repository, and the users that work on that repository only have a local working copy of the data, which represents one snapshot of the files that is stored in the repository. Users can then perform changes in their working copy, commit the changes that they have done to the repository, and from there other users can check them out, perform their own changes, commit them back again, etc. Now, today the most popular systems are distributed systems, which have a peer-to-peer-like architecture. So the most popular ones are Git and Mercurial, and here we do not have a central repository anymore, but each user stores a local copy of the repository, and consequently the commit operation is only local operation, and we have additional operations that allow users to synchronize their repository with others. So we have the push operation, which allows Alice, for example, to push her changes to Bob's repository. Then Bob can perform a local checkout, and Carol can even pull Alice's changes from Bob's repository, perform some changes, and push them back directly to Alice. Now, it's still possible to have a central repository in these systems, but it's not technically required, but we can use it for convenience. For example, the users can use some code hosting platform like GitHub or Bitbucket to synchronize their repositories. And while we use subsequent numbers to identify revisions in centralized version control systems, we typically use cryptographic hash values of revision's actual contents to identify revisions, because we need something that is globally unique. Now, the scenario that we consider for our work is that of confidential files. So suppose Alice has some confidential data that belongs to a project, but that she does not want to share with all the other users that have access to the repository. This could be, for example, a configuration file of a software project that contains database credentials or access tokens, and in this example, she only wants to share this with Carol, but not with Bob. Now, this is possible in principle in distributed version control systems, as Alice could just make sure that this data is only synchronized, only committed to her local repository and synchronized with authorized users. But the problem here is that this would limit the typical workflows in these systems. So Carol, for example, would no longer be able to pull Alice's changes from Bob's repository, and we even could not use a central repository anymore, and that this is completely trusted by all the users. So the only meaningful solution would be to encrypt the data in some way so that only authorized users can decrypt them. But unless we have explicit support for that by the VCS, this would be somehow limited. So the users would have to do the key exchange manually. The workflows would get more complex, and the users would have to ensure that they never ever commit unencrypted data to their repository by accident. And if we use the standard randomized encryption scheme for that, we also would incur a lot of overhead at the VCS could no longer perform data deduplication. So that's exactly the problem we try to tackle with our work. We integrate transparent end-to-end encryption of confidential files into distributed version control systems. And the challenge was to do that in a way that all the existing workflows are maintained, that we remain compatible to existing repositories of unencrypted version control systems, and we also wanted to preserve storage efficiency. So in the next 20 minutes, I will first show our security model, then present our concept with respect to confidentiality and authenticity guarantees, and afterwards I will give some words on our implementation, present some evaluation results, and finally conclude the talk. Now, the security model is as follows. We consider a number of users that have access to some repository which they share with one another, and first of all, if we only have revisions in that repository that contain only non-confidential files, we do not provide any security guarantees at all, which go beyond that of the plain version control system. But as soon as we have at least one revision with at least one confidential file, then we provide confidential security guarantees with respect to each individual confidential file. We consider the user that commits a confidential file as the file's owner. That is the only user that is allowed to change the confidential file's access rights in our extension. So Alice could, for example, grant a write right to the user Bob and a read right to the user Carol. Whenever she changes the rights, she has to commit a new revision of the file. She can also change these rights over time. So, for example, revoke the access right from Carol and grant an access right to the user named Dennis, and yeah, that's how it works. Now, with respect to each individual revision of each confidential file, we provide the following security guarantees. We guarantee confidentiality of file names to the extent that only users that have access to at least one revision of a confidential file are able to see the file's name. Confidentiality of file contents to the extent that users require a read write for a specific file revision to be able to see its contents. We provide authenticity of file names to the extent that we allow only the file owner to change its name, and authenticity of file contents to the extent that only write-authorized users can create successor revisions of a confidential file if they have the right one, as said before. So the confidentiality concept is as follows. As said before, the idea is to encrypt the file content and also the file name. So for the detailed concept, we basically have to answer these four questions. We have to decide on keys that are used for encryption. We have to define where and when encryption shall take place in the system. We have to handle key distribution, and we have to choose appropriate encryption schemes. The first one is easy. We simply assign a random symmetric key to each confidential file that is created by a user. Regarding the second question, it might seem obvious to perform encryption and decryption during push and pull operations, as this is the boundary that confidential data is not allowed to pass. The problem here would be that this would require extensive changes to the version control system's internal data structures. We would have to change the repository presentation, and to avoid that, the idea is to perform encryption and decryption already during commit and checkout operations. So let's have a more detailed look at this. The idea is we split the working copy that is used by the version control system into two layers. We have a regular working copy layer, which corresponds to the working copy which is seen by standard version control systems, and we have a virtual view on top of that that is allowed to contain decrypted data of confidential files. First of all, if the user checks out just a revision with non-confidential files, then these revisions are checked out into the regular working copy, and that's exactly what happens in the unmodified version control system. So the virtual view is identical to the regular working copy. but as soon as we check out a revision which contains confidential files, then we check these encrypted representations of the confidential files out into the regular working copy in a specific area which is hidden to the user, and then we process the encrypted representations, we decrypt them according to the user's access rights, and then create decrypted representations only in the virtual view, and there the user can work on the files just as on regular files. So she can perform modifications, she can even create new confidential files, and as soon as she wants to commit her changes to the repository again, the representations, the decrypted representations are encrypted again, so the encrypted representations are updated, and then only the contents of the regular working copy are committed to the repository. Now the confidentiality, third question is again an easy one. So luckily all the common distributed version control systems have already support for OpenPGP certificates, so users can use the OpenPGP certificate to sign revisions that they commit. And so we decided to just require the users to have an OpenPGP certificate whenever they want to access confidential files. And that way we can use the user's public keys to encrypt the keys of confidential files that the user had access to distribute these keys. Now, regarding the encryption scheme, we simply encrypt file names using a standard encryption scheme. So we use a randomized encryption scheme, AES-CBC in this case. Regarding the file contents, they tend to be much longer and therefore qualify for the version control system's data deduplication mechanisms. For that reason, we do not use randomized encryption for that, but instead use some specialized encryption scheme that allows for data deduplication. This scheme is adopted from prior work, which focused on the centralized version control system. So I'll only sketch its key aspects at this point to show how it works. The main idea is to split the file content into a number of chunks, which are then deterministically encrypted in a way that they can be deduplicated by the version control system. For the first step, for this chunking, we use a dynamic chunking scheme based on a rolling hash function, which works as follows. We consider the first couple of bytes of the file content, compute its hash value, and then we move this window to each byte of the file content, and whenever we find a position whose hash value meets some specific condition, we create a chunk boundary at that point. That is done for the whole file content, and finally we have a number of chunks. The reason that we use dynamic chunking instead of static chunk sizes just is that this scheme is resistant to insertions and deletions. So if we insert a character quite at the beginning of the file, for example, we will just affect the first chunk because chunk boundary is determined based on the content. And the only thing that could happen is that two chunks merge or split up due to a change, but all the remaining chunks remain unchanged and therefore can be deduplicated. In the second step, we encrypt the individual chunks using deterministic encryption. Actually, we use convergent encryption for that, which works as follows. We take the file content, compute a hash value for the content, which is keyed by some additional key, the conversion secret, and then we use the resulting hash value to actually encrypt the chunk content using a deterministic encryption scheme, and then only the chunk key that we computed is actually encrypted with the file key. So the reason that we do that instead of deterministic encryption is that the ciphertext of the chunk is unchanged even if we change the file's key, which we need to do when access rights change. Yeah, and in the last step, we concatenate all the encrypted chunks at an authentication tag, and together with some minor additions which are not shown here, the scheme can actually be proven secure and is able to allow for data deduplication. Now, regarding the authenticity concept, our goal was to provide authenticity of both file names and contents, and as we already require our users to have OpenPGP certificates, it seems obvious, or it is obvious to require the users to sign all modifications that they perform and store these signatures in the repository. The detail, so they are signed, and again we do that during commit and checkout operations, so after encryption and before decryption. And the details, of course, are a bit more complex, so let's have a look at this. First of all, if Alice wants to create a confidential file, we represent that confidential file using two objects. We have a data object which corresponds to the file's content, and a metadata object which contains metadata like access rights and file name. And first of all, Alice generates a random identifier for that file. Under this identifier, the encrypted file is then stored in the regular working copy. And she assigns the access rights, so in this case, she's only set as file owner. Afterwards, she generates the file-specific key at random and encrypts it with the public keys of all authorized users, so only herself in this case, and then she uses this key to encrypt the file's name and content using the encryption scheme shown before. And finally, she adds the base revision based on which the confidential file was created to the metadata object. This is just to prevent replay attacks, and then adds a signature for the metadata object, and then base revision was added to the data object for the same reason. We include a hash value of the metadata object to tie the data to the metadata, and then a signature is added as well, and all of this is committed to the repository. Now, when Alice wants to change access rights, she simply has to modify the access rights in the metadata, and of course, she has to renew the file's key, which she re-encrypts with all the public keys of users that are now authorized. Then she re-encrypts the file name using that new key and creates a new signature for the metadata object. Again, she updates the base revision to prevent replay attacks, and then the data object is updated accordingly. So again, the file content is re-encrypted, base revision is added, and a signature is computed, and then everything is committed to the repository. Now, Alice just granted a write access right to the user Bob, so Bob is now able to perform changes to the file content. To do this, he just actually has to change the file content, re-encrypt it using the key that is known to him, so he already used it for decryption, and then again he updates the base revision for the same reasons as before, and then Bob computes a signature for the data object and commits only the changed data object to the repository, while the metadata remains unchanged. Now, all users that have access to these files are able to verify authenticity. For this, it is not sufficient to verify the signatures for an individual revision, but they actually have to check the whole version history. So when Dennis wants to check out the file, he has to verify each individual revision that is in the repository with respect to authenticity of all contained confidential files. For this, he first of all has to check the signatures, that's clear, and he also has to check for sanity, so he basically has to check whether the base revision pointers are correct. This might take some time during an initial checkout, but these results can be cached locally by the user, so since revisions are mutable, he only has to perform that once per revision. Now, if we have a large number of users that have access to the same confidential file, it may get impractical to require them to trust each other. And instead of requiring trust between all pairs of users that have access to a confidential file, we only require trust between file owners and individual users. So if Dennis wants to check Bob's signature, he just has to trust Alice, as Alice granted the access right to Dennis. Alice has to trust Bob, as Alice granted an access right to Bob, but the trust from Dennis to Bob is established transitively using the metadata, which is signed by Alice. So here, where we have the access rights, we actually store the fingerprints of their OpenPGP certificates. Now we have implemented the whole concept into the Mercurial version control system, which is available for download right now. And yeah, its usage is almost transparent to the user, so we have introduced an operation for creation of confidential files, some operation that allows administration of the access rights, but all the encryption and decryption, etc., performs transparently to the user during commit and checkout and other operations. So he doesn't even notice that if everything is set up correctly. Regarding the storage structure, we store all the encrypted representations of confidential files, which are part of the regular working copy, in some hidden subfolder of the repository and working copy. And we have another hidden folder in the working copy, which contains some local management data, like cache verification results, which is only part of the virtual view of the user and excluded from all operations of the VCS. Now, to get a feeling for the storage efficiency of this extension, we have repeated an experiment that had been performed for the centralized version control system SVN before. So we basically replayed the version history of some open source project into a fresh Mercurial repository and measured the storage requirement after each commit. And the blue line here shows the storage requirement for an unencrypted Mercurial repository. This clearly has the lowest storage consumption, as the VCS can perform both data deduplication and also compression on the contents. The purple line here shows the results that we had if we simply encrypted each individual revision of a confidential file using a randomized encryption scheme without using our extension. So this is much more overhead. The red line shows what happened if we used our extension together with randomized encryption. So we see the overhead for the metadata management and access right management that we have here. And finally, the green line shows the storage requirement if we switch from randomized encryption to the specialized encryption scheme. So the savings, as we can see, are actually significant. And the dotted lines show the results for SVN for reference. And as we can see, Mercurial is more storage efficient than SVN in any case, which is simply due to a different storage architecture. We've also performed some micro benchmarks to see the computational overhead of the extension. For this, we have chose a number of very small files from the Linux kernel repository and just committed the last 100 revisions of each of these files and measured the time. As we can see on our test machine, we require about 50 milliseconds for each invocation of an operation just to load our extension into Mercurial, and then we require about 50 milliseconds for each confidential file revision that is to be committed or encrypted, and for verification we need about 23 milliseconds per file revision that is verified. And to account for larger files or file sizes, we have repeated the experiment with much larger files. As we can see, verification time is almost unaffected by this, but the time for encryption is much higher. which is due to the specialized encryption scheme, which is rather computation intensive. Now to conclude, we have seen a concept for storage of confidential files in distributed version control systems, which is almost transparent to its users. It allows file owners to define access rights for confidential files, which are then enforced cryptographically, and we establish trust between users, partly based on OpenPGP's Web of Trust. Yeah, and we have an implementation, prototype implementation for that, which is already compatible to unmodified Mercurial versions, so it can be used on top of existing repositories and can be combined with cloud hosting platforms, and it is available for download right now. So that's it. Thanks for your attention, and now I'm ready to answer questions.
Yes, thanks a lot for the nice presentation. We have time for some quick questions. Who wants to be first? Yeah.
Hi, thanks for your presentation.
Just a simple question, please. It's regarding your model that you presented today. We have different access control models such as DAC, MAC, role-based access control. What is the added value that you have done in comparing with? Because you said it's about performance, something to do with the performance of encryption and decryption. And this is not 100% accurate because sometimes the encryption actually takes time based on the key value, how big it is. Thank you.
So the encryption that we perform is just symmetric encryption, and so it's actually quite fast. What takes time is what needs to be done for the data deduplication. So the chunking scheme that we use is rather computation intensive. The access right model, the contribution is that it actually matches the workflows and data structures of the version control system. So we, for example, could not modify access rights of confidential files or confidential file versions that are already committed to the repository, since we cannot change any information that is stored in the repository with respect to existing revisions. So does that answer your question?
Yeah, because you can make another copy of the file, so this way you can't stop. There is no any way to stop the other user making another copy. So I was a bit like you can't stop them having a second copy.
Yeah, that's true.
No, I think you probably hear what I said. Yeah, because we need to find a mechanism, like Alice is protecting her files. I tried to access her files illegally. She probably gave me some permissions, but I can abuse these permissions and just take another copy of that file and do whatever I want to do. Thank you.
Yeah, I can create a copy of the file and then this. So just a moment. A copy of the file under the same name, just to.
It doesn't matter, different name. I can call it
Okay, so I have to actually use a different name. I can just create a copy and grant access rights to new users. That's okay, that works. But for users to actually access the copies, they have to trust my keys. So the users can see that I am now the owner of the file. I cannot fake that this file belongs to Alice. So users can see that.
Okay, thank you. There was one more question over there.
Actually, thanks for the talk. I have two questions. The first one is, there are a lot of numbers for your evaluation. Can you just say, what is the speed down? So is it twice as, if I do it without encryption, without security, is it double of the time I need, so speed down of 2 or whatever? That's the first question. And the second question is, you did a symmetric encryption scheme, right?
Yeah.
Could you have done it asymmetrically as well? Why have you chosen to do it symmetrically in your design?
I would say for performance reasons, but it's actually quite slow. So it's works. So do you see advantages in asymmetric encryption with respect to data deduplication and so on?
No, I was just wondering, because you use a asymmetric public key cryptography anyways, right?
Yeah.
Why couldn't I, if I know I'm working together with 2 users and I want to grant some access to this, I could directly create a group, like you do it with normal PGP, and then do it asymmetrically. And I was just wondering if you have considered this as an option and said you don't want to do this. If you say just for performance, it's fine. But anyway, my first question: how much slower is it? Factor 2, factor 5, factor 10? There were a lot of numbers, but how much longer do I have to wait?
So as for encryption, it's hybrid encryption actually.
Yeah.
So it's standard. The slowdown, it depends on the file size. So
yeah, so huge file size. If I want to, I think this is quite small what you did, right? So you have really tiny ones and you have a bit larger ones. But what happens if I use a big whole repository from a software project, let's say 200 megabytes or something?
So the thing is, you use the extension to encrypt some files of a repository. So what we evaluated is to encrypt all the files, but that's not what one would do in practice actually. If we had a file of size 200 bytes, so with this encryption scheme, it's about 5 megabytes per second that we can encrypt on a standard machine, but this actually can be optimized, so the implementation is Python, and yeah.
Okay, thanks a lot. One more final question. Yes, over there, please.
Okay, so first, thank you for your interesting talk. I don't quite understand why you need the chunking scheme, because as far as I see it, every user that can write a file also has read access to it. So couldn't the system use a normal deduplication or diff and then encrypt the patch?
This would be possible in principle, but again, it would require extensive changes to the version control system. So the protocols are to commit the data to the repository based on the file that is actually stored in the repositories. And by using that chunking scheme, we can just use a repository at some cloud hosting platform, which doesn't even need our extension. So it's only effort that has to be done on the client side.
Okay.
Okay, thanks a lot. Is there a really urgent final question? No? Then I would say thank you again to the presenter.